Welcome to this new lecture on hybrid force motion control. We have seen that there are two conditions under which we model and control the interaction between a robot and the environment. The first involves compliance at the contact and leads to the design of impedance control. The second assumes that the environment is infinitely stiff and constrains the motion in some direction. So in this lecture for hybrid force motion control design, we will consider this second situation when the robot is in contact with a very stiff environment, so infinitely rigid in principle, maintains contact so that there are natural constraints acting on the end effector motion, which may be considered as bilateral one. So we cannot penetrate the environment with the end effector of the robot, but also we don't want to lose contact because otherwise we would fall in a different category of control tasks. Now, we have already seen that there's a possibility of considering such bilateral geometric constraints within the dynamics and obtain a constrained dynamic model or a reduced dynamic model where we eliminate the extra degrees of freedom and remain only with the independent degrees that allows motion. So what is new in this context? There are some differences when we are dealing with hybrid force motion control. I just remind you that we have seen, for instance, in the modeling using the reduced approach, where we eliminate the m of the generalized coordinates associated to the constraints, so we have a reduced dynamics of n minus m differential order. So in that case, we have also designed, we have seen that that approach is suitable for designing the feedback linearization and decoupling approach so that you can control in an independent way through simple integration or even no integration both the constraint forces that arise when you attempt to violate the geometric constraints and the free motion. Now, what are the differences at this stage? First of all, we still design the hybrid control law imagining we are in ideal condition. We will see what this in particular means. But now the direction where we have constrained forces and unconstrained motion will be defined using a special formulas which involves a task frame, a usual frame that is associated to the task. So it will be more direct to visualize. The second, and more important, is that we will consider non-ideal condition. So we will apply the control law designed in this way, but that takes care of the fact that the surfaces are not infinitely stiff, so they are not rigid. There could be some compliance at the contact, and this compliance may be originated not only by the environment, but also from the contact type, the presence of a force torque sensor, and so on. Moreover, while in geometric setting you don't consider friction at the contact, so while you're moving in contact, there's no force dissipating energy, we will also have take into account this to understand the performance of the hybrid force motion controller. And last but not least, indeed, if we have some geometric uncertainty, so if there is error in the orientation, for instance, of the surface at the contact where the robot is making contact with the environment, what will happen? So the hybrid force motion control implicitly include a filtering on the measured quantity. I would call this geometric filtering, which makes sure that things remain consistent with respect to the model. So essentially, certain direction in which we don't expect that signal arise, for instance, in the direction where we hit the surface. So we don't expect to have motion in that direction because the model assumes an infinitely stiff environment. We may have some velocity still because of a number of reasons, and we will just filter them out. And similarly, along the free direction, we don't expect any opposition to motion, but the presence of friction may in fact reduce the speed that we are having in contact. And again, we will not consider forces that are being measured in that direction, which are associated, for instance, to friction. And we will just treat those extra components, if, of course, they are not too large, as disturbances to be rejected by the control design. So, in a sense, the hybrid control laws avoids that we are trying to do two things at the same time in the same direction, namely controlling forces and controlling motion because of the measurement that we are receiving from the real system. So this is a very important point that will be clear later on. So with this in mind, in the literature, there has been a consideration of two types of constraints. This may be misleading because in fact the second type of constraints is not really constraining at all, but this terminology now is in use. So first of all, we assume that there are ideal conditions, so both the robot, the environment, and the contact are perfectly rigid, and there's no friction at the contact while the robot is moving in that area. So under this condition, there are, we can identify some generalized direction, in fact divided in two complementary sets, and this direction defines the so-called task space. So you can imagine, and we will see a slide later on, that there is a joint space where we do actuation, the Cartesian space associated to the frame attached to the end effector, for instance through a Denavit-Artenberg convention, but there's also another frame that could be defined typically in the Cartesian space, but which changes accordingly to the interaction task and moves along with the operation of the task. So this generalized direction, there are in fact a total of 6 if we are dealing with the general tasks that involve position and orientation in the Cartesian space. So out of this 6 direction intended in a generalized sense, so a direction is in fact a combination, it's a 6-dimensional vector combining linear quantities and angular quantities. We will be more clear in a moment. So there are 6 minus k direction along which we cannot have any motion. So not a linear motion with a speed v, with a velocity v, nor an angular motion with an angular velocity omega. Why we cannot move in that direction? Because the environment will react there, building reaction forces or torques at the contact, so that the end effector cannot move in that set of direction. And then there are other directions where the environment is not able to generate any reaction forces. This will be complementary to the previous one, so there will be k such direction, so that the robot in that direction is free to move, but on the other side we cannot try to apply forces in that direction because the environment will not react to these forces, and so these forces will be transformed into acceleration. There will be no balance between the forces that we are trying to apply in those directions and the reaction of the environment by the principle of action and reaction. Now, these constraints that limit where we can have reaction forces or where we can move have been called natural constraint on force and motion, and they are associated to the task geometry, so in particular to the way in which the end effector is interacting with the environment. Now, this is, let's say, a qualitative description, how we characterize this direction. Well, this is done through the definition of a task frame, which we call reference frame with a subscript T in general, and the axes of this frame will specify which are this direction. So imagine that we have a generic robot, this is a cloud, in contact with a generic environment represented as another cloud. So typically we place a task frame at the contact. If the contact change in position and orientation, the task frame will move accordingly, at least in the planned interaction task. And along this frame we can define several, the axis of this frame, along and around, several quantities, actually 12 quantities. So there are linear quantities along the x, y, and z axis. These are the component of the velocity, vx, vy, and dz, and the component of the force, fx, fy, and fz. The velocity should be intended as those of the end effector of the robot, the forces as those that the environment applies in reaction. And similarly, around the x and y axis, we can define the three components of the angular velocity, omega x, omega y, and omega z, and the three components of the momentum or torque, mx, my, mz, generated by the environment. In general, such task frame is placed at the end effector of the robot. Now, with this in mind, there are also artificial constraints in this framework. Now, this artificial constraint, as I said, may be misleading because they are in fact a way in which some researcher, in particular Mason, treated the problem of control. So, in the presence of the natural constraint, we may execute our task in different modalities. So when we specify the way in which we execute the task, we are in fact imposing some constraint on the total behavior. This is in fact the target of our control problem. So the way in which the free end effector velocities, linear and or angular, in the k direction where feasible motion can occur are specified, and similarly how the contact forces along and around the 6 minus k direction where the environment can produce reaction are being specified. So these are the reference for the control. We generate error with respect to these references in a number of directions which covers the whole space, so 6 minus k for contact forces and torques, and k for end effector linear and angular velocities. So a total of 6 when the Cartesian space where the robot is executing has dimension 6. Of course, there will be sub-cases where this value of m equals 6 is strictly less, so for instance, planar task or something like that. So these two sets of direction, as I said, are complementary, so they cover the 6-dimensional generalized task space. Why 6-dimensional will be clear in a moment. And they are independent within each set and mutually orthogonal. So when we make a scalar product between a 6-dimensional contact force torque, which is a reaction force torque of the environment, with an admissible velocity, linear and angular velocity of the end effector, this product will be 0. So this set of forces torques with the set of end effector velocities will produce no work, in fact. Moreover, the task frame can be time varying in the sense that if we have a contact of an end effector on a surface and we move the end effector on this surface, accordingly, if the task frame is placed at the end effector position, the task frame will move. It may change orientation or not, depending on the geometry of the environment. So we say colloquially that the task frame moves while the task execution is in progress. So why 6D? Because in fact we are using in a friendly way, I would say, the mechanical concept of screws. So screws are six-dimensional vectors, which are the stacking of either linear and angular velocity, so these are called twists in general, if you have a six-dimensional generalized velocity vector of this kind, or wrenches if you stack the forces, so linear quantities, and the torque, so momentum, also said, one on top of the other. These are six-dimensional vectors, and they are called in a unified way wrenches. So twists and wrenches are in fact particular screws, and there's a mathematics of screws connected to that. But we will not, I mean, I'm mentioning this, but we will not get into the detail of this formalism, but we will see that in fact what we are doing, we are using twists and wrenches in a proper way. So let's do a few examples in order to understand how natural constraints, or also called geometric constraints, are associated to a particular interaction task, and how artificial constraints are specified accordingly, and what are the choices that we can make there. In this few slides, I'm presenting three examples of increasing complexity. You will see that the robot is not there at all. In fact, we don't need to specify at this level what type of robot are we using. We assume that the robot has enough degrees of freedom to perform the task. If not, of course, some of the specification of the interaction task cannot be met by control. But everything deals with the way in which the end effector, and so I'm representing here the end effector in this particular slide as a gripper holding an object in a firm way, is interacting with an ideal environment. I remind you that the environment is stiff, so infinitely rigid, and has no friction at the contact. So it's a purely geometric one. So this is very similar to what we have seen in the reduced or constrained robot dynamics, but here we are using the concept of task frame. In fact, for this task, we have a cube that should slide along a guide. The guide is constraining, in fact, the motion. We could move up the cube with the gripper, so robot going up in the z direction, but then we will lose contact. So we assume that we keep this type of contact all the time. We can place a task frame, so a reference frame with a subscript t. In fact, the x, y, and z axis should carry also a subscript t, but in order not to overload the notation, I just kept them as such. So as you can see, you immediately see if you how to place the frame at the contact. In fact, if I slightly rotate, for instance, this frame, which is the correct one, indeed you may replace the order of axes the way you wish, but so you can exchange x with z and so on. But this is the correct frame. If we imagine to rotate a little bit around the z-axis this frame, so that the axis is no longer aligned with the guide, and the y is also rotated as well, then you can imagine that the free motion of sliding along the guide would not occur exactly in one of the axes. So the choice of one axis along the guide is mandatory. And similarly, the other two axes are chosen once you have chosen x in this way, so that there are pure force or motion components that can occur along each of these axes. So this is the choice of the task frame for this case. And let's see what are the natural constraints. For a matter of energy consideration and of work consideration, these are specified in terms of linear velocity or force and moment, or force and torque. So there are 12 quantities as a whole, and we will see that these 12 quantities, so 3 components for each of these 4 vectors, belong either, are constrained naturally, so geometrically constrained from the interaction, or artificially constrained because we can assign to them any desired value. So let's start with the natural constraint. As you can see from the picture, indeed we cannot move in the y direction with a linear motion, so By is imposed to be equal to 0. Similarly, Vz is equal to 0 because we cannot go against the bottom of the guide, but as we said, this becomes also bilateral constraint because we imagine not to move up the cube, so to detach one of this side from the bottom of the guide. So Vz is equal to 0 as well. Similarly, you really cannot move around the x-axis or the z-axis because the side of the cube are in contact with the side of the guide, and this will prevent any rotation around the x and z axis. On the other hand, there are 2 natural constraints on the reaction forces that the environment can generate. Since we assume that there's no friction in the contact, the environment, so this guide embracing the cube, will not be able to impose a reactive force along the x direction. So the x direction is in fact free to move, free for motion of the cube. If we try to impose a force by control in that direction, the cube will simply accelerate because the environment cannot balance any desired force there. So we would make a mistake if we try to control force along the x direction. And similarly, the cube, in fact, in this situation, would be free to rotate around the y-axis. We don't want to do this because we will like to execute the task as specified, so we would like to slide, and this will appear, in fact, in the artificial constraint. But for the time being, we understand that if we rotate the cube, trying to encounter a momentum resisting to this motion from the environment is not able to produce any momentum, any torque around y to contrast this type of rotation. So, as you can see, there are 6 quantities being specified by the natural constraint, and these are in fact 4 of the motion type and 2 of the generalized force type. Now, what are the artificial constraints? You should proceed really on a complementary way. So all the quantities that have not been involved individually in the natural constraints should appear in the artificial constraints. So as a rule of thumb, if you have a linear velocity along the y direction among the natural constraints, so this is constrained to be 0, and this is very important, this structural 0, then the linear force along that direction, so Fy, will appear among the artificial constraint, namely to Fy, and this is the first equation that you see in the red box, can be assigned any desired value. What does it mean? That we could impose that the cube slides correctly along the guide while pushing against a side of the guide along the y direction, positive or negative. So we could impose through control that the contact force and the reaction that the environment generates accordingly will be any positive or negative value Fy desired. Indeed, if we want to avoid internal stress, we could set this value to 0, but this 0 is different from those above because, in fact, it's a specification. No? We could set any value. If we want to perform in a reasonable way this motion, we would set Fy desired in particular equal to 0. And same story, we had angular quantities, omega x, omega z, as motion constrained in the natural set. Then the associated torques or momentum around the x and y and z axis will appear as the artificial constraint, meaning that we can assign any value mx desired or mz desired to these quantities. For instance, let's look at the mz desired. What would this mean is that through controlling, commanding the robot properly, we could try to apply a momentum, trying to rotate the cube with the gripper around the z-axis, apply a momentum to the environment which would then react, no matter which momentum we are trying to apply. So mz desired could be positive or negative, but if we don't want to have internal stress for the cube and for the environment, we could set this reasonably equal to 0, and same story for mx. Now, again, we had a linear velocity along z in the natural constraint, so we will have a linear force around z being specified by the artificial constraint, so as a reference for the control system. So we are setting, I'm setting here a generic Fz desired will be positive probably, so that this guarantees that while sliding and pushing a little bit on the bottom of the guide, we will guarantee that a sliding condition occurs rather than a rolling condition. And similarly, we would be free to rotate the cube around the y-axis, so we can specify an angular rotation or angular speed, omega y desired, but since we would like to execute exactly the task by sliding the cube, we will set this value to 0. So we are free to choose any desired value, but in order to perform the task correctly, the reference should be 0 angular velocity around the y-axis. And finally, this is the most obvious thing, we could move fast or slow, we could stop, reverse motion, and so on, while sliding the cube along the guide, and all these specifications are embedded in a desired linear velocity Vx desired along the x-axis. Now you can see that we have, in fact, out of the 12 quantities, 6 are in the artificial constraints, and in particular there are k equal to free motion which are being specified by the controller along the Vx and the linear velocity along the x-axis, so Vx, and the angular velocity around the y-axis, so omega y, while the remaining set, 6 minus k, so equal 4, are of force or momentum nature. And in a complementary way, there are 6 minus k directions, so k is 2, so 4 directions which are constrained for motion of the robot and the effector and in contact, when expressed indeed in the direction of along and around the direction of the axis of the task frame. And complete this, there are 2 directions where the environment cannot generate reaction forces. So as you can see, the picture is quite nice in this way, but how can we use this in order to formalize things? In particular, we formalize a way to specifying the generalized direction, so 6-dimensional vector, that where free motion can occur, and those complementary directions where the environment can generate reaction forces. So we will do this for this example in this slide. So first of all, feasible motion. So we consider the 6-dimensional vector, in fact, a twist of stacking the 3-dimensional linear velocity with the 3-dimensional angular velocity. And we say that all feasible motion, so those that comply with the geometry, with the natural constraint of the environment, are those that are along the x, linear x, and angular y direction. So we can write this simple relation in this case, in which we say that we can consider any generalized velocity for the end effector, but those that are associated to feasible motion have only this direction. You see, it's a kind of identity, so any vector v can only have the structure of 1, 0, 0, so have only a component around the x direction if the motion is, we are considering only the feasible motion for this interaction. And similarly for the omega. So you can see that these are in fact two columns can be organized in a matrix. Let's call this matrix T. This matrix has 6 rows always, and k equal to columns, which are in fact the number of free directions that we are considering. So we can parameterize any 6-dimensional vector by the product of t times the two scalar vx and omega y. In a complementary way, we can parameterize all feasible reactions, so the direction along which the environment is able to produce forces or torques. And as we see, these are along the linear direction y, the linear direction z, and the angular direction x and the angular direction z. So similarly, if we take a generic reaction vector, 6 dimensions, so in fact a range composed by the 3-dimensional force F and the 3-dimensional torque M, then this 6-dimensional vector can be generated only by a combination of 4 parameters, which are the scalar Fy, Fz, and x and m and z. So we are selecting in fact direction. So we will never have a force which has a component Fx as a feasible reaction force, because the first row of this matrix is equal to 0, so we don't parameterize this motion, which is in fact not, this reaction force, which is in fact not being generated by the environment in the task frame. So again, you see that we have elementary column of zeros and 1, with the 1 only in one position, and we can call this matrix, which is always 6-dimensional and which has always 6 rows and has a number of columns which is equal to 6 minus k, so 4 in this case, we label this matrix Y. So in fact, this particular choice for this simple example of T and Y, these are constant matrices. In general, they may not be constant. And they are in fact picked out as columns from a 6 by 6 identity matrix. I'm using selection. We are selecting and placing in the proper order those columns, because in fact the terminology of selection matrices was the one that originally was used within the hybrid force motion task formalism. So we'll see that this can be in fact generalized, and in the third example this will be very clear. But one thing that should be noticed, which is very important, is if you take the scalar product between the transposed columns of matrix T and the columns of matrix Y, you will get this identity. So T transpose Y is equal to 0. So the columns of T are orthogonal to the columns of Y. And this is always the case in this modeling of the interaction, because in fact reveals that reaction forces and torques, so F and M transpose, will not perform work on feasible motion. Now this is written in the reverse way, but it's the usual way that we do things. So forces, momentum as a row vector, and velocity, linear angular velocity as a column vector. Well, of course, you can transpose this and you obtain the same results, and this is what the product T transpose Y is saying. So rows by linear and angular velocity, and columns by forces and momentum. So this is a very important relation, which guarantees that we are making a consistent model, because reaction forces do not produce work on feasible motion. This is the concept when the contact is rigid. Of course, I should never forget the underlying assumption. Let's consider a second example, a little bit more complex, which is, in fact, sorry, just one moment, which is turning a crank. We have seen that this is a classical example of a hybrid control problem, so where forces and velocities are involved at the same time. So in particular, we consider the case of a free handle. So the handle can rotate around the blue z-axis as written here. Now, I've put a reference frame. It could be at the base of the robot or just at the center of the crank. It's not really important here. And this is fixed. Now, where should we put the task frame RFT? Well, as we said, it's at the end effector level and should be oriented in such a way that along and around each of its axes, so x, y, and z are the axes of the task frame. Again, I discarded a subscript t, which is for compactness. So around and along this direction, we could specify something either in terms of linear angular velocity or in terms of linear forces and angular momentum. So the one possible choice is this one, with the y direction along the tangent to the circle that is being traced when the crank is rotating, is being turned. And you see that this task frame changes in position and orientation while doing the task. The previous case, of course, while the cube was sliding, the frame was moving together with the cube, but not changing orientation at any time. Here, instead, we have also a change of orientation, which can be represented with respect to the fixed zero frame by an elementary rotation matrix around the z-axis, of course the z-axis, the z0 axis in this case, by an angle alpha, which progresses with the task execution. So this becomes what I said at the beginning, should become more clear now. The y direction has been chosen because we know that we will have, while rotating, a tangential velocity along that direction, and x and z are chosen to complete the frame, but also considering that, for instance, along the x direction there will be no motion possible, okay, because the gripper and therefore any robot which is behind this gripper will not be able to move along that direction because while firmly holding the crank. Now, the natural constraints are the following. Again, 4 constraints on motion quantities and 2 constraints on generalized forces. So we cannot really move along the x direction, so Vx is equal to 0. Since we are firmly holding the handle of the crank, we cannot move along the z direction either, so Vz is equal to 0 again. Remember that those 0 are structural, so are not choices, are really limit the motion at the contact. Similarly, we cannot rotate around the x and y axis because the handle and the crank are rigid bodies, so we cannot rotate in that around that axis. But the environment, in fact, cannot oppose any forces applied along the y direction, because in fact this is a free motion direction. And since the handle is free to rotate and there is no friction, remember the assumption, the ideal assumption at the contact, also there is no momentum that the environment, so the crank, can generate around the z-axis. So this completes the set of 6 natural constraints, 4 bars motion and 2 describe the direction where the environment cannot generate reaction forces or momentum. Now, complementary to that, we will have the artificial constraints. Again, the first 4 are on completing the 4 motion quantity in the natural constraint. There are 4 quantities of force and torques in the artificial constraint that we can assign at will. But all this value, fx desired, of z desired, and x desired, and y desired, will be set to 0, although we could force, for instance, push the handle in the x direction or pull it, but we will produce only stress. So this is an undesired type of contact, unless we would like to really try to destroy this type of contact. So these values are set, could be arbitrary, positive or negative, but are set for a convenient execution of the task to 0. Now, complementary to the 2 quantities that are among the set of natural constraints in terms of forces and momentum, we will have the possibility of specifying arbitrary values for the linear speed along the y direction, so Vy desired. This is the tangent speed of rotation. If you want to rotate at 1 radian per second and the crank has a radius of 2 centimeters, we will have the product of 1 times 0.02 meter per second. So 0.02 meter per second will be the speed along the tangent to the circle. It could be positive, stop, negative. Of course, this will describe the way in which we want to rotate the crank, if uniformly rotating in the same direction, or moving in one direction, stopping, reversing, and so on. The last specification for the controller, so the last artificial constraint, is on omega z. In fact, omega z can take any value. If we set omega z desired to 0, it means that this handle, which is free to spin, should not spin in the way we execute the task. So while we're moving around, there will be, let's say, one side of the handle which will always be exposed toward the center of the crank. This means omega z equal to 0. Indeed, because it will move together with the frame, the task frame. Instead, if we would like to keep the orientation of, let's say, the angle around z of the free handle constant with respect to the 0 frame, indeed, we should specify an omega z which is associated to this type of behavior. So these are all the right-hand side values of this artificial constraint can be specified in general at will and will be associated to a different way of executing the task. Now, even in this second example, we can parameterize the direction of free motion and parameterize as well the direction where the environment is producing reaction forces or torques. We will use again the formulas with the T and Y matrices, but now we will have a slight change because we are in fact having a task frame which is rotating with the angle alpha. So if we write things in the zero frame, so in the absolute frame, so a linear velocity and an angular velocity as expressed in this frame, we will have that the selection is being made in the task frame, so we can only have a linear velocity along the y direction and angular velocity around the z direction. So you can see the second matrix with zeros and 1, and multiplying the two parameters dy and omega z, which, as I said, parameterize the only feasible motion at the contact. But in fact, if we are writing these quantities in the zero frame, we need to rotate the associated velocities by the R alpha matrix transpose. In fact, we are this is the orientation. R is the orientation matrix of the task reference frame. So when we are expressing quantities from that frame in the zero frame, we should use the transpose of this rotation matrix, and of course there's a rotation for the linear velocities and a rotation for the angular velocities. So if we combine these two matrices, one with the two rotations and the columns of constant column of 0, 1, we obtain matrix T, which is a function of alpha, so it changes with the execution of the task. Now, complementary to that, we will have also the generalized forces and torques that the environment can produce as reaction. So again, if we are writing things in the zero frame, we will have first selecting columns from the identity matrix with ones and zero that specified which are the direction along which we can have reaction forces, or around which we can have reaction torques, so Fx, Fz, and x and y. And then this reaction range should be expressed in the zero frame, and so should be rotated by the same quantity. So the resulting Y matrix, the product of the two matrices in this second formula, will be also a function of alpha. But no matter how, this property still holds. You know, when you do the transposition of the rotation matrix in T of alpha, will not carry the transpose, and we multiply directly the transpose matrix in the range. So this will be eliminated, and what matters in fact is only the orthogonality of the 0, 1 columns of T, which becomes in fact rows of T transpose, and the 0, 1 columns of the matrix Y. Okay. The last example is the more sophisticated that I will present. Of course, many more can be considered, which shows that we really need to work with screws with 6-dimensional vector. And to understand also the terminology of screw, let's consider a task where we are really inserting a physical, real screw into a bolt. Now, you know that there are several standards for building screws, so that you can use them all over the world. And one of these parameters is the so-called screw pitch. So it's the distance between one spiral and the next one along the screw. For instance, 0.5 millimeters. Of course, you can use Anglo-Saxon units in this case many times. So again, there's no robot here. There's only a gripper holding the screw from the top. And we are already imagining that we have started the insertion, so that the type of contacts and interaction can be characterized by a reference frame, which is the red one now, with the z-axis pointing downward or upward would be exactly the same. So it's still a right-handed reference frame. When we're doing this, we understand, just before introducing the equation, or the natural and the artificial constraint, we understand that while we are progressing with the task, so the screw is being inserted in the bolt, it cannot keep the same orientation. So the linear speed at which we progress inserting the bolt, the screw in the bolt, will be associated to an angular velocity as well, because of the existence of the screw pitch. Now, it would be different if we were inserting, let's say, a cylinder, so a peg in a hole, which has not this bolt type spirals. So in this case, we could progress by inserting with a certain speed while keeping the orientation, or while specifying also an angular speed along the z-axis. So the situation is completely different in this case. In fact, if we start with the natural constraint, we can write those that are clear. For instance, that we cannot have a motion along the x-axis, neither along the y-axis, which are normal to the insertion direction of the screw in the bolt. So these four quantities are zero. And indeed, there are two missing quantities here to be completed. Okay. What about the artificial constraint? Since the previous one were partial, these at this stage are abundant, in the sense that there are some relationship among those quantities. And in fact, assuming, again, this is very important at this stage, that there is no friction at the contact, so the bolt is not feeling any friction, which is counterintuitive, because we know that in order to screw or sometimes unscrew the screw in a bolt, we may need to apply a force exactly in those directions. But since this is a geometric modeling, let's see what this specified. So indeed, we can push the screw on the side of the bolt in x direction and y direction, and again try to rotate the bolt around the x and y axis, but this will not be possible because there will be a reaction, forces and a momentum that will oppose this type of motion. If we want to achieve a perfectly tuned insertion, we could set this value to 0. Then we can set an arbitrary positive velocity VZ desired that associate the progress of the insertion, the speed of this insertion, and accordingly we will have an angular speed. And this angular speed is in fact specified by the speed, the linear speed at which we are progressing. In fact, the relation is very simple. The omega z desired cannot be chosen other than as Vz desired multiplied by 2 pi over p, which means if you have a pitch of 0.1 millimeter and you're progressing at 1 millimeter per second, or 0.1 millimeter per second, then p and Vz will simplify, and in 1 second you will have done a full rotation of the screw. So this is the reason of this simple formula. So you can this is the problem at this stage. So on one side you can specify Vz desired, but then you will have automatically a free omega z which is being specified accordingly, or vice versa, you can specify a desired angular velocity around the z-axis, and automatically you will specify a linear velocity for the progression of the task. So this is quite obvious. So there's something that should be eliminated here, and in fact should be parameterized in a different way. The artificial constraints are completed. Of course, we can have we can apply, sorry, just one moment. So we can apply a force along the z-axis, and this is in fact true because we have the side of the bolt inside that opposes forces, but accordingly we will have also a momentum, and this momentum will be a function of Fz design. So this is critical, and here we could be lost if we would like to express directly this relationship. But we will see that the formalism of feasible motion and feasible reaction forces will help us immediately. So the problem here is the following. So this is not a complete description. It's not a correct description because you can proceed along, the screw can proceed along and around the z-axis, but indeed these two motions are not independent, and in fact there's only one degree of freedom that should be parametrized. And similarly, this type of linear forces and momentum around along and around the z-axis cannot be independent either. So the idea is that we should remember that the range direction of the reaction forces and momentum should be orthogonal to the feasible motion twist, so linear and angular velocity. And this will help in understanding how to select direction or quantities. In fact, in this case, we will not select direction as columns of the identity matrix, 6 by 6 identity matrix, but we will need to combine linear and angular quantities as intuition says. So, how do we do this? Now, in order to have more space in the slide, I've written the column of T as a row to be transposed. So all linear and angular feasible velocities, so the parametrization, are parameterized just by one quantity. We can choose which one to use, either Vz or omega z. In this case, I've chosen Vz. And in fact, there's only one degree of freedom which is allowed for motion. And this motion will be a combination of a linear and angular progress. So in fact, the twist, so a rototranslation around and along the z-axis. So this can be parameterized in this way. So all feasible v omega are specified by Vz and occur in the z direction of the linear quantity in motion, and in the around the z direction for the angular motion, with a special factor, which is exactly the factor that relates Vz to omega z. Of course, we could have put a 1 in the last element of this vector, and accordingly we would have we would have parameterized things with omega z, and accordingly we would have had a p over 2 pi in the third component. So this is your choice. Now, how do we complete the 5 directions along which the environment can react? You know, remember that the sum of the free motion direction and of the reaction direction should sum up to 6. So we will do this by looking for the maximum, the matrix which the maximum number of independent columns, namely 5, that lies in the null space of the T transpose of this row vector that you see on top of the slide. So this is very convenient because it's very easy to compute that. You can do it also in MATLAB. And this is the solution. So where are the zeros? You will put the 1 so that you have a direction which is certainly in the null space. So the first column of the Y matrix contains a 1 in position 1 associated to the 0 in position 1 of the T transpose vector. The second one will be in position 1, and similarly another one in position 4. Second one will be in position 2. and then again a 1 in position 4 and position 5, so that these produce certainly 0. And finally, an orthogonal vector to the 0, 0, 1, 0, 0, 2 pi over p, which is, for instance, the one with the minus 2 pi over p in the third position and the 1 in the last position. So again, we have this matrix. It has clearly independent columns, so it's our Y matrix, and all forces and momentum here. Forgot to change the notation into small letters instead of capital letters. Sorry for that. I will correct this in the slides. So fx, fy, and mx, and y, and z are parametrizing the 5-dimensional space of reaction wrenches. You see that from that column, that row, that the forces along the reaction forces along the z direction is a factor minus 2 pi over p of the momentum. So this is the way in which you can relate things. Of course, you may have used also the fz to parameterize that, but then the matrix, so mz would be a function of fc, indeed from the same formula. And you can use fz in place of mz to parameterize the task. In any case, you can see that the columns of t and y do not necessarily are selection of the columns of the identity matrix. In fact, they are generalized screw direction in the 6-dimensional space. So I think that this last example specifies better what's going on. So now we move from this example to the general formalism. Before doing that, we need to focus on an application issue, namely, what are the frames of interest involved in this hybrid task? So consider, for example, a planar case. So now we are living in a m equal 2-dimensional space, in the Cartesian space, and we have a point contact on an environment surface of a generic form. Now, where are the tasks of interest here? Where are the quantities being measured? In particular, the green block on the end effector represents a force torque sensor, which is now measuring only forces in the plane of motion. The contact is pointwise, so there could not be any momentum associated with that. Although indeed there is a momentum if you apply a force at the tip, and if you're using the frame associated to the force torque to the force torque sensor, yes, you will experience also momentum around the z-axis. But in fact, we will use a frame which is a different one. So first of all, the task frame. The task frame. Okay, here they are. The task frame is the red one with the one axis aligned with the tangent, and another axis along the normal to the surface. Indeed, along the xt direction, we will be able to control motion, so it's a free motion direction. Along the yt direction, we will command a contact force if we want to apply a force for some technological reason, for instance, for removing extra material from this surface, so the debarring task, but we cannot move, in fact, along the yt direction. So Vx in frame t desired, the scalar, will be the reference for the feedback control law, and a force along the normal direction, so Fy desired in task frame T, again m minus k, in this case again a scalar, will be the reference for the feedback control loop on force. Now, the sensor frame here has been moved from the sensor, exactly for the reason that I just mentioned, is measuring the two linear forces Fx and Fy, in fact, rotated with respect to what we expect. So even if everything is ideal and we are experiencing only a force along the yt direction, the sensor will produce measurement both in the ye and xe direction, in fact the direction of its own reference frame. Similarly, when we are computing velocities, in particular we are computing velocity at the contact point, so along the xt and yt direction, and we are doing this by using the encoders and the differential kinematics, so the Jacobians and the joint velocities, of course. But when we compute j of q times q dot, and we have the linear velocity, in this case we will use a 2x2 analytic Jacobian if we wish. These velocities are in fact expressed in frame 0. So there's a base frame where we express velocities. So again, even if we are going in the right direction along the tangent, so along xt, indeed we will see component of velocity along x0 and y0 in both directions. So in order to understand if we are doing things correctly, so to generate an error and to react to this error, we should really move these quantities of the force or motion type all in the same frame. So we should in fact rotate and generate error in the same reference frame, which is in fact the task frame. So this will be clear when we associate a block diagram to our generalized hybrid force motion control. So this is a very important thing. Please understand it correctly. Otherwise, you would select quantities which are correct and you expect that they are in fact, you believe that they are in fact wrong. So now to the general parametrization of the hybrid task. We need through the task frame, and in fact we are describing implicitly the type of contact, so the feasible motion, and this will be parameterized by a set of variables which we collect in S, and in fact S dot will be in fact the parameterization of the speed. In general, both the T matrix and the Y matrix will be function of this parameter, which is associated to the progress of the task. As we have seen in some cases, T and Y will be constant, so there's no parameter, but this is the more general format. So we will have K parameters for describing the admissible free motion, the feasible free motion, and accordingly a set of m minus k parameters, which we call not by chance lambda, because they are associated to the parametrization of reaction forces and torques at the contact. So any generalized twist d omega of the end effector can be described by a number of k parameter s, and with s dot and the matrix T. And similarly, any wrench reaction Fm can be described by a set of m minus k parameter lambda through the matrix Y. And because reaction forces and torques do not perform work on displacement, so linear and angular displacement of the end effector, the condition is that T transpose Y is equal to 0, so that T and Y, the columns in this two matrices, T and Y, are orthogonal to each other. Not orthogonal inside them, but orthogonal to each other. Okay, so this is the starting point. Indeed, the previous example, and more in general, we will have m equals 6, so the task will be defined in the full three-dimensional space, Cartesian space. In the previous example, where we have introduced for as an exemplification the frames of interest in this hybrid control problem, we have used m equal to, but in general m is equal to 6. And later on we will assume that the robot has at least, or exactly, n equals 6 degrees of freedom in order to do computation. Of course, if the robot is redundant, all the things that we know about redundancy can be applied as well. But don't anticipate things at this stage. So we add to this what? Indeed, we need the robot dynamics. Which dynamics? The one which included generalized forces or wrenches in our formulas applied to the end effector. So on the right-hand side of the Euler-Lagrange equation, we will have the command U generated by the motor torques, and then J transpose, the Jacobian, the geometric Jacobian in this case, multiplying a generic wrench. Now, this is true even if we are not in contact. We are pushing the end effector with forces and torques, but indeed, when we will be in contact, F and M should be parameterized by y of s lambda, and so we should substitute this inside this equation. So robot dynamics is important, but also robot kinematics. So not surprisingly, V and omega are the linear and angular velocity of the end effector with the geometric Jacobian J of q multiplied by q dot. So with q dot, in general, we may generate a twist in any direction, 6-dimensional direction. But indeed, when we are in contact, then V and omega cannot be arbitrary, but should be parameterized by the previous formula T of S times S dot. So we should replace this into this equation. And this will be used for making the full derivation. Now, what is our with this parametrization in mind, what is our hybrid force velocity control objective? I'm using now velocity because instead of motion, because as we have seen, orthogonality is in terms of velocity and reaction forces. But indeed, you can use both terminology as well. So the control objective is hybrid, so we would like to impose some desired evolution on time to the parameter s, which parameterized with s dot the feasible velocities, so feasible motion. But at the same time, we would like to assign a value to the parameters lambda, which parameterize forces, and again, this could be any trajectory over time. So this is our task, to bring S to the desired, or to keep or bring, if we have a reaction, or if we have errors on these quantities, S to S desired and lambda to lambda desired. And the transient of error should be the nicest possible. No? If we are able to achieve this by feedback linearization, so the error behave as linear with linear dynamics, and the convergence would be specified, would be exponentially and not just asymptotic. We have already in our background this type of concept, so I will not insist on that. Now, in fact, we will design the hybrid force velocity control using feedback linearization. So, again, in two steps. The first one will linearize and decouple exactly the behavior, but now in a different frame, not in the joint space, not in the Cartesian space, but in the task space, so in the space where we have put the task frame. So we'll use nonlinear feedback in order to do this, and the closed loop model will be exactly the one described in the yellow box. So the acceleration of the parameter s will be specified by a new input a of s, and the value of the parameters lambda that specify the contact forces will be assigned by another new input A of lambda. Now, once we have obtained this, and we will see how to do this in the next slide, we will complete the control design by a linear specification of AS and A lambda, as we have done before, and we will impose a desired dynamic behavior to the, let's say, motion error and to the force error. Let me use this generic terminology. So, in the following, we will make the assumption that n is equal to m, usually 6. As I said, if n is larger than m, we will have redundancy, so we can achieve the hybrid force velocity control task. And in addition, we should specify joint torques in the null space of the task in order to, let's say, I don't know, avoid obstacle or get the best manipulability configuration, and so on and so on. The other assumption that we make is that the geometric Jacobian is square and it's not singular during the execution of the task. Now, remember that in simple cases, as the first example that we have shown, in fact, S dot and lambda, this parameter, are just single components of S dot of the linear or the angular velocity, v or omega, and lambda are just linear components of the force or of the momentum. So you don't need to think of a parametrization which is complex. You can use directly these components, and accordingly, the matrices T and Y will be what has been called in the original literature on these topics as selection matrices. In fact, 0-1 selection matrices. So they are columns taken from the identity 6x6 matrix, organized properly among those that describe feasible motion and those that describe admissible reaction forces. So, how do we design the feedback linearization in the task space? This is subtle, but then straightforward. First of all, you start from the kinematics, as usual, I would say. So, you describe the linear and angular velocity on one side from the robot mode, from the robot side, so using the Jacobian of the robot and its joint velocity q dot. But on the other side, you're describing the same velocity as those that the type of contact allows to exist, so the feasible motion. So they are described by T of S times S dot. Now, suppose that we drop dependence from now on for compactness or recover when really needed. Now, this is true. So we cannot generate any V omega with the q dot in a given configuration Q with a 6x6 matrix which is non-singular, but in fact we should constrain the motion in such a way that the feasible velocity of the end effector are parameterized by the T matrix times S dot. So if we differentiate over time, we will have a relationship in terms of acceleration, so J Q double dot, I'm dropping dependence now, plus J dot Q dot on one side, on the robot side, should be equal on the same quantity described from the interaction type. So T S double dot plus T dot S dot. And from there, in the assumption of non-singularity and of a square Jacobian of the robot, we can isolate the acceleration, so J to the minus 1 times T S double dot plus T dot S dot, bringing the other term, the minus, to the other side, so minus J dot Q dot. And now this acceleration, no wonder, will be substituted in the model, in the dynamic model. First of all, in the dynamic model, as I anticipated, the generic wrench acting on the end effector is substituted by only the admissible wrench due to the contact. So Fm is being parameterized by Y S of lambda.
and you can recognize something from the constraint dynamics that we have considered in the geometric case. There was a constraint Jacobian. In this case would be J transpose times Y. The only thing is that we are parametrizing Y by the S, which describes the progress of the motion of the of the interaction task. So now we take Q double dot and we place it where it appears in the dynamic model. And now we can reorganize things. So we replace this, and we reorganized, in fact, the inertia matrix. Now, when we substitute Q double dot, we will have an acceleration terms in terms of S double dot, so we will have m times j to the minus 1 t. Now I'm reintroducing dependencies for clarity, times S double dot, and then we will have the parametrization of contact forces. So we will put this into this, let's say, hybrid inertia expressed in the task frame. So this will come from the right-hand side of the dynamic model. So J transpose Y brought to the other side is minus J transpose Y times lambda, and then all the other terms, those coming from the acceleration again. So m J to the minus 1 times T dot S dot minus J dot Q dot, and then the standard Coriolis and centrifugal term and gravity term from the model. And what remains on the right-hand side is only the applicable torques, so the input torques U at the motor. So there's one basic consideration here that needs some comment. This matrix, which I called the inertia matrix in the task space, the hybrid inertia matrix, because you can see that there are inertial quantities on the first set of columns and non-inertial quantities in the second set of columns. However, this 6 by 6 matrix is non-singular under the assumption that we made, so that the geometric Jacobian of the robot is non-singular, and that T and Y are orthogonal to each other. In fact, this matrix is a 6 by 6 matrix in our case, and the columns of this matrix are independent. You should prove this. In fact, you can obtain this matrix, and I leave you this as an exercise, but you can obtain this 6 by 6 matrix as the product of a 6 by 12 matrix, which has the first 6 columns as m j to the minus 1, and the second 6 columns as minus j transpose. And indeed, this 6 by 12 matrix is full row rank, so it has rank 6, multiplied by a 12 by 6 matrix, which has the first 6 rows with the T matrix and a 0, and the second 6 rows with the 0 and the Y matrix. Now, being T and Y linearly independent, containing linearly independent columns, this 12 by 6 matrix has full column ranks equal to 6. So you have a product of a 6 times 12 times 12 times 6 matrices. Both matrices have the right full rank, so the resulting 6 by 6 matrix, which is the one in the slide, will be full rank, so non-singular. And this is very important because we will not inbreak this, but we will eliminate this from the picture when we design the feedback linearizing control U. In fact, how did we design this? By taking this matrix and multiplying it by new input A of S and A of lambda, and cancelling all the rest. So the linearizing and the control law is in fact one specified here. So the same hybrid inertia matrix in the task space times the new input AS and A lambda, and then all the remaining terms that are being cancelled. Of course, you need to know the good model, dynamic model of the system in this case. And this is the standard assumption that we make for feedback linearization. So the result is what expected, as I said. S double dot will be equal to S, A of S, the new input, and there are K of such equation, and this is a second order differential equation, by the way, while there are M minus K set of equations which are algebraic equations. You don't see any derivative there, which specify lambda through the new input A of lambda. So if you had taken S and lambda as output of your nonlinear system, and you would have applied the inversion algorithm that we have seen for the Cartesian control in the free space, you would have ended up by taking enough number of derivative of your output until the input appears, and in fact we have now a difference, because we have to differentiate the motion output S twice until the U will appear, and in fact this is what we have seen from the above equation. So this set of output has, each component has a relative degree equal to. We have already introduced this concept. On the other side, if we take lambda as output, immediately you will find the U acting on it. You cancel all nonlinearity and you obtain lambda equal A of lambda. So lambda as an output has a relative degree 0, because you don't have to take any derivative of lambda. This is good because taking derivative of lambda means in a somehow taking derivative of the measured force, and the force torque sensor is relatively noisy, so you like to avoid taking derivative of force, but this is not needed under our assumption. So now that you have linearized and decoupled the system, as usual, you apply linear control techniques in order to stabilize the tracking error. I'm talking about tracking error, but of course you could have regulation task where S desired and lambda desired remain constant. But you will do this on each decoupled input-output channel. So for the motion channel, we will use AS as the desired acceleration of the parameter S, plus a PD law, and KP and KD will be chosen positive, definite, and diagonal as usual, so that the error defined as SD minus S will satisfy this linear and decoupled differential equation, second order differential equation, which will let any error in S and in S dot converge exponentially to 0. Same story for the algebraic loop. And we will choose this, deserves some comment, this control loop as the desired parameter lambda desired, which specified in fact the contact forces and moments, plus an integral terms on the error between lambda desired and the actual lambda. Why we are doing this? In fact, this implies that the error defined as the difference between lambda d and lambda goes to 0 as long as ki is positive. We will again choose ki as a diagonal matrix so that we keep the decoupling. But why did we add this integral term? In fact, since the relation lambda equal A of lambda is algebraic, we could have chosen simply A of lambda equal to lambda desired, and this would be enough. But in this way, we would have introduced, let's say, no force error in the control loop, although we were controlling explicitly forces. So adding this integral term does not destroy stability. In fact, this is shown by the linear analysis, very simple analysis of these two formulas. but will give more robustness in the presence of constant disturbances that are not being considered. For instance, if you have along the contact direction a force related to friction or to an incorrect orientation of the surface, then you will keep, this will act typically as a constant disturbance, and this will be rejected by the integral term. So it's very convenient to use this. On the other side, you don't put derivative on this, because derivative of the error in lambda would involve lambda dot, and therefore some derivative of the measured forces which we would like to avoid. This is about all we need, but if we look at this equation, we should understand how to realize those control loop, and in fact, how to get information on S, S dot, and lambda, which appear in the yellow and in the green box. Indeed, the desired values have been chosen by the artificial constraint, so by our way of executing the task. But then, in order to close error loops, we need actual measurement. So we need to extract S, S dot, and lambda from the actual measurement available on our system. Which are these measurements? Indeed, we can measure, we assume that we measure the configuration Q by encoders. We can assume that we measure, although there's no direct sensor for that, also Q dot by a numerical differentiation of the very accurate encoders. And we have also force torque sensor mounted at the end effector. So from these quantities, we should extract the actual value of S, S dot, and lambda. And by doing this, we will also filter out all the components that are non-consistent with the geometric model, the ideal model of the interaction. How do we do this? So, first of all, S and S dot will be obtained from measure of Q and Q dot. And as we have seen for the design of the controller itself, we will equate the pose and also the generalized velocity from the robot side, so described by the direct kinematics and by the differential kinematics with the Jacobian, with the same description from the environment side, which is a function of S and S dot. So S indeed for the pose, and S dot for the velocities. It's difficult to make a general treatment at this stage, but I will show this through a simple example, exactly the robot turning the crank. So, where is the end effector position? This is described from the robot side by the vector r with respect to frame 0. Now the frame 0 has been placed in this point, but it's irrelevant, just not to design the robot itself. From one side, from the robot side, there will be some kinematics f of 0 of q. However, from the interaction side, this is parametrized by S. In fact, if the crank has a length L, the actual position of the end effector is L cosine of S and L sine of S, and a 0 because you're working in the plane x0, y0. In any case, it's constant while you're rotating the crank. So from here, from the measurement of Q and from the value of the direct kinematics, f of Q expressed in frame 0, so these are numbers at this point, you can extract the value of S by doing an arctangent of f of y and f of x expressed in frame 0. A very simple example, but this is the general procedure that you would apply, and of course, case by case, robot by robot, you will have this type of extraction. What about S dot? This is more simple once you have S, so you equate the linear velocity from the robot side and from the robot environment interaction side, this equation was already found before. Remember that suppose that the robot has, as we have considered so far, 6 degrees of freedom, and the task is 6-dimensional in fact. So you have a 6 by 6 Jacobian, which is invertible, although you don't need this at this stage. On the other side, T is a 6 by K with K less than 6 matrix. So if you want to isolate S dot, you need to do a pseudo-inverse of T. So you will have T pseudo-inverse times J Q dot. I will come back to this in a moment. So now that you have S and S dot, what about lambda? Well, lambda is related to contact forces, so we will use the force torque measures from the force torque sensor at the end effector. And again, we will use the basic relation of the parametrization of these forces. So we assume that anything that you measure, and this is in Fm, should be described by y times lambda. Now let me comment on this immediately. Indeed, you may at some point have measurements that are not in the span, so in the range of the matrix Y, so could not be captured by a lambda. So if you solve for lambda in this way, so making the pseudo-inverse of this matrix Y, which is again non-square, so it's a 6 by 6 minus k column, 6 rows and 6 minus k columns. So you do the pseudo-inverse. In this case, you will minimize the error on what you measure and on what you can express through your modeling stage. So every time, for instance, you have an uncertainty, you can measure forces that are not in the span, but you extract in a consistent way lambda by doing this pseudo-inversion. So both pseudo-inverses are of tall matrices. So this is exactly the opposite case of redundancy. No? So we have more rows than columns. And assuming that these T and Y matrices are full rank, the pseudo-inverse can take a closed form. For instance, for the T pseudo-inverse, we will have the T transpose T to the minus 1 T transpose expression. Indeed, we can use singular value decomposition more in general. We could use also, instead of simple pseudo-inversion for extracting S dot and lambda from this equation, we could use a weighted pseudo-inversion, take into account uncertainty and other aspects. But this filtering, in any case, is the one that accompanies the implementation of hybrid force motion control. And this is completely absent when we are returned to the original constraint dynamics that we have dealt with. So we are really looking at the practical aspect, the non-idealities, and the filtering aspect is part of the game. So let us summarize this in a block diagram and stop here for the moment. So you can see various blocks with colors. So I will refer to colors. You start with the robot which is in contact with the environment. So your inputs are you, and your output, I mean, of course, you measure Q, you measure Q dot, or please indirectly through numerical differentiation of Q, and you measure F and M with the force torque sensor mounted on the end effector. Now, however, these are not the quantities that you're interested in. Because of our parametrization, our output are in fact lambda and S. So the one that are outside the filtering of measurement. So the open loop system goes from, let's say, the 6 torques U generated by the motors to the 6 quantities, in fact M equals 6 in general. 6 minus K will be lambda and K will be S. So same number of input and same number of output, but in fact this model is highly nonlinear because of the nonlinearity of the robot and because of the nonlinearity of the environment model, the way in which it constrains the end effector and generate contact forces, and also coupled. So if you move one of the joint torques, you will affect, in general, all lambda and all s. So what you do is you apply the task space feedback linearization that we have seen before. This is the first step of our control law, of our hybrid control design. So now, between the new input AS and A lambda in front of the yellow box and the output S and lambda out of the light green or olive green block, we will have linearization and decoupling. In particular, double chains of integrator on each component between each component of AS and each component of S, and an algebraic relation between each component of A lambda and each component of the output lambda. Okay? Now, the remaining part of the block, so the blue and violet lines and gains Kp, Kd, and Ki, are in fact the linear design. So, for instance, for the M minus K force control loops with the diagonal and positive Ki, we are generating A lambda with the desired component lambda desired of the parametrization of forces and torques at the contact, plus the integration of the error between lambda d and lambda. And this is represented by the violet loops, and there will be M minus K force loop in general. M equals 6 is the standard case. On the other side, we will have for the motion input AS, this will be generated by the desired acceleration of the parameters that are describe the feasible motion, and then with the Kp of the error Sd minus S and the derivative term Kd of the first derivative term Sd dot minus S dot. Indeed, I have separated this, so I have the blocks on the feedback loop and I have a combined feed-forward terms, but if you recombine these things, you have exactly desired acceleration plus PD of the error. Now, this block diagram is quite general because there are limit cases. For instance, if K is equal to M or 6, then there will be no force control loop. There will be only motion involved, and this is just the parametrization of the free motion. So this type of control or block diagram applies, for instance, to Cartesian space feedback linearization. So the task frame will be the natural frame associated to the end effector, no need to specify it. And along each direction, you will impose in a decoupled and linear way the desired motion. So the limit case when K is equal to M are free motion and the control that we have seen in the Cartesian space. There's another limit case which is probably less relevant. Is it when K is equal to 0? So there will be no motion control loops and there will be M linear and decoupled force control loop design on the linear side of this task. Now what does it mean? We are only controlling forces. That means that the robot end effector cannot go anywhere. It's like frozen in the concrete, so we cannot move, and so there makes no sense to assign a motion to the end effector. But indeed, using the torques produced by the motors at the joints, we can regulate or assign any time profile to the contact forces and momentums acting on the end effector, because this end effector is fully constrained by the environment. As I said, like if you're putting a solid block of concrete around the end effector, and indeed the robot will not move. If the robot has extra degrees of freedom, it can reconfigure its configuration, but indeed not move the end effect. So this limit case is of little relevance, but shows that we can have a full range of possibility by moving k from 0 to m. And when it's positive and strictly less than m, let's say 6 in the general case, then we will have really a hybrid control problem. And this way of approaching things is a very successful one. Let's make a break and we will continue considering the special case of selection matrices. So when the T and Y matrices included in the task-based feedback linearization and in the filtering of measures are simply column of the selection matrix, so columns of the 0, 1, 6 by 6 identity matrix. Thank you for listening.